Warning: nitric acid is corrosive. Nitrogen dioxide gas is toxic. Work in a well-ventilated area. Hi guys, here is MIH. In my last video on making hydrobromic acid, I mentioned my EE and IE projects. The acid was for my IA, but today's synthesis of 10 rare earth nitrates is about my EE. You guys can guess what my EE topic is. Hint, it has been done on YouTube a couple of times before, and of course, the other hint is that it needs so many rare earth elements. Anyways, I made these 10 nitrates not only for my EE, but just because I like the rare earths. I've already done quite a bit of rare earth chemistry on my channel that you basically can't find anywhere else, at least not on YouTube. However, these videos only focus on the light rare earths, the ones on the left of the lanthanides, such as cerium and neodymium. Today we're going to explore the more rare, more precious, and more mysterious heavy rare earths, which encompass the right side of the lanthanides, as well as the non-lanthanide element yttrium, since it usually mixes in with these heavy rare earths in minerals. These metals are much less reactive than the light rare earths and have distinctive appearances and optical properties. Alright, let's get started. I first weigh out roughly 1 gram of each of the 10 rare earth metals, which have the atomic numbers 62 to 70, in addition to yttrium at 39. The lighter rare earths didn't have the optical properties I want, and they are much more reactive in metallic form, so these metals are usually not put up for sale. Scandium and lutetium are the two most expensive rare earths, and they also don't have the properties I want. The general trend of rare earths is that the elements in the middle have cool optical and chemical properties, while the ones on the sides are boring trivalent metals which give colorless ions. Anyways, you can see that I got considerably less holmium and erbium samples than other metals, and the samples of europium, terbium, and thulium weigh very close to 1 gram, while all the others are slightly off but not too off. The reason for this is actually not just because I'm lazy to weigh out 1 gram of each metal, but instead it is very interesting and relates to the cost and properties of rare earths, which I'm again pretty sure nobody else has talked about on YouTube. The explanation is rather long, so if you're just coming for the chemistry and the cool colors, feel free to skip forward. The price of rare earth metals varies considerably as seen from this table I made. Note a few things. 1. Generally, the price of rare earth metals is at an intermediate level between commodity metals and noble metals. I've included the current price of silver as a comparison, and you can see that the price of rare earths is similar to it. This is mainly because of two factors combined: the abundance and concentration of rare earth elements, and the rather complicated refining process of rare earth metals. Rare earths, despite their names, are not rare at all, and as you can see from the graph, the abundance of cerium in crust is the same as copper and nickel, and higher than many other cheap and common elements like bromine, tin, and mercury. Additionally, rare earths usually form concentrated minerals that can be easily and cheaply extracted from, such as monazite and bastnasite. These factors combined render the cost of extracting rare earths rather low. However, the main cost lies on the separation and refining of rare earths. As the properties of rare earth elements are so similar, specialized technology like ion-exchange chromatography and solvent extraction must be used to separate most individual elements. Some rare earths, such as cerium, have distinctive chemical properties, for example valences, and can be separated easier, which explains cerium oxide's very cheap cost compared to other rare earth oxides. Once compounds of pure elements are obtained, they must be further reduced to metals, which adds on the cost even more, since rare earth elements are known to be very reactive. Their standard electrode potential is in fact much lower than aluminum and approaching magnesium. The more abundant and reactive light rare earth metals are usually extracted by molten salt electrolysis of rare earth chlorides, or rare earth oxide dissolved in molten hydroxide, which, by the way, I want you to try someday. The heavy rare earth metals are usually produced by silicothermic or calciothermic reactions, which use silicon or calcium to reduce the corresponding metal oxides and fluorides respectively. Samarium, europium, and ytterbium, sometimes also thulium, have much lower boiling points and higher reactivity due to their nearly half-filled or fully filled f orbitals, so they are instead produced by reductive distillation using a mixture of their oxides and lanthanum metal, which I thought was a very insane and cool process. You put some pieces of lanthanum and some samarium oxide in a tantalum crucible, then put the crucible in an induction furnace, pull a vacuum to a millionth of an atmosphere, and distill over 99.5% pure samarium that forms gorgeous dendritic crystals. How cool is that? And you can see this dendritic appearance very obviously on the sample of ytterbium and thulium as well, and maybe a little bit on yttrium. That was my first point, that the cost of rare earth metals are justified due to their production processes. My second point from this table is about the cost of individual elements. The difference in cost between the cheapest, samarium, and the costliest, scandium, is over 100 times. This honestly shocks me, since as we've seen earlier, the abundance of rare earth elements doesn't have that much of a difference. Additionally, rare earths do not have that many applications, and while the ones that do have a few usages such as neodymium, europium, terbium, and dysprosium are rather expensive, elements like scandium and lutetium really have no significant use, but they're even more costly than the actually useful ones. So only from the consumer side, there's no reason why the cost of rare earths are like this. So I don't know what is happening from these prices, but there might be some unknown difficulties in industry that renders the price of these metals different. Apart from the rare earth elements' cost and appearances, another significant physical property of them is their magnetism. According to literature, most of the heavy rare earths are paramagnetic, meaning that they are attracted by magnets. And indeed, gadolinium is very strongly attracted to magnet, and weaker attractions are observed on dysprosium, holmium, and erbium. Terbium and thulium are also supposed to be observably paramagnetic, but since I've already loaded them into vials, their paramagnetism aren't that obvious. As seen from the table, the magnetic susceptibility of gadolinium and terbium are significantly higher than that of other lanthanides, which corresponds to its much more apparent paramagnetism. Apart from paramagnetism, gadolinium also has quite strong ferromagnetism at room temperatures, meaning that it can act as a magnet and attract other objects, but it loses its ferromagnetism at its cured temperature of just 19 degrees C. I didn't test it here, but I'll certainly play around with it in the winter when it can be seen visibly magnetic. But anyways, finally back to the experiment. I have here a beaker of deionized water, and I added around 5 ml of water to each of the vials containing the rare earths. Samarium didn't react significantly with water, but europium reacted very vigorously, giving off hydrogen and forming europium 2 and 3 hydroxide. All of the other elements didn't show reactivity against water. It is known that the reactivity of lanthanide elements decrease as the atomic numbers increase, and since most of the elements we have here are the heavy rare earths, they're not that reactive towards water. However, europium is a significant exception, as it has a half-filled f orbital electron shell in its divalent on state, which leads to its high reactivity and high tendency to form divalent compounds. An analogous but diminished reactivity can be observed on ytterbium, which has a full f orbital electron shell in its divalent on state. Under the protection of my fume ventilation device, I then carefully added 4 milliliters of 70% nitric acid drop by drop into each vial to dissolve the metals into their nitrates. I made a big mistake to directly add 2 ml of acid into the samarium vial, and the reaction got a little bit too vigorous. But samarium is the cheapest of these lanthanides, so I really don't care. As you can see from the vigorous reaction and the evolving nitrogen dioxide, the europium didn't completely react with water. The dissolution of the other rare earth metals proceeded similarly, evolving nitrogen oxides and giving clear solutions. When the metals don't seem to dissolve anymore, I add a few more drops of nitric acid to the vials. It looks like I'm running in an underground factory that makes wizard potions of different colors, but I'm really just a home chemist dissolving a bunch of very cool rare earth metals. When nearly all the metals finish dissolving, I'm left with a beautiful array of 10 rare earth nitrate solutions, each with cool colors. I place the vials on a hot plate and gently boil them to drive the reactions forward and dissolve all of the remaining bits of metals. At this point, I like to point out that the color of rare earth ions exhibits some sort of symmetry. The recorded color of trivalent rare earth ions are shown in the table here, and if you imagine starting from the two ends of the series and moving to the center, you can see that the colors are similar. For example, both lanthanum and lutetium are colorless, praseodymium is green and thulium is yellow, while both neodymium ions and erbium ions are pink. As of my knowledge, there are no explanation for this currently, so who knows, maybe someday one of us will propose a theory that explains this. However, the colors from the table varies rather significantly with the real colors that we observed here. Apparently, gadolinium and dysprosium has a slight yellow tint, erbium's color is more orange-red than pink, thulium's color appears more green than yellow, and ytterbium also has a yellow tint. I don't know if these variations in color are due to impurities in the metal or simply because of dissolved nitrogen dioxide, maybe even both. But the one thing we can learn from this is that color descriptions in literature are often not that accurate and strongly dependent on subjective judgments, so don't rely on this. The final test I did was shining UV light on the solutions to observe the fluorescence. Europium has an extremely strong red fluorescence, and terbium has slightly weaker green fluorescence, but I saw neither. So it's either my UV is at the wrong wavelength, or it's because my stuff isn't pure. But judging from the vigorous reaction of europium with water, it's more likely that my UV light is bad and I should get some better ones. But that's for another project. Stay tuned for the next stages of my EE, and thank you for watching.